Welcome back to everybody. I hope you had a nice little break. So this is our last week. We're going to have, class 3 more times, I suppose, and then the final exam. So we will, as usual, have a quiz on Friday, which will cover the stuff that's on the homework. We have a homework due tomorrow, and the quiz on Friday, as always. And I hope everybody's clear on how the final exam works. So after the quiz on Friday, I will grade it as soon as possible, and then you will know which of the things you have checked off on your big list. And if you've already got them all checked off, then that means you're done and you don't have to take the final exam, and your grade in the course will be A, probably, although remember your checklist is averaged into your homework score. So it is possible, if you have a terrible homework score, even if you get all the checks, you might not finish with an A, but this is probably not going to happen. Anyway, I would expect for most of you, you will end the week after the quiz with still a few questions that you want to do, and so you should come to the final exam and do just a few questions. The final exam is scheduled for 3 hours, so you have plenty of time. Probably you will not use all the 3 hours. And it may be because of your just average overall, like in order to get an A in the class, you need 93% overall. So that means actually you don't actually need to get all the check marks in order to finish with an A. So after the quiz, I will look at everybody's grade and I will let you know if you don't have to take the final exam. I suppose, technically, nobody has to take the final exam. If you don't take the final exam, you just get whatever grade you had after the quiz. So if you're satisfied with an A-, I suppose you could skip the final, although I don't suggest that. Anybody have questions about that? I hope that this makes sense to everybody. Yes?
What time is the final?
I don't remember. It says on the syllabus, and it's also on our website where the homeworks are.
Because I was looking on the schedule and the predicted final, and then it said 11.
Yeah, I think it's 11:30. Did I say 12:30?
Was it 12:30 on
Yeah, I think on the syllabus it says 11:30, and I think that's correct. I will, if it says 12:30, I'll change it. It should be 11:30. Sorry, were you really banking on a 12:30? No, all right. I told somebody once the wrong final exam. I told him the wrong day. He got really mad and called the president of the university. Yeah, it was. Yeah, not a good situation, although I already had tenure. And it was better for me that he called the president and he was like screaming at him on the phone. So like nobody took him seriously, even though, I really did mess up. But yeah, he went crazy about it. That's a little pro tip. If your professors ever screw you over, you should complain. Don't complain. Don't go crazy. Then they won't take you seriously. I didn't really screw him over, though. All right. Any questions about anything? No. Let's continue. We're talking about power series. That's what we were doing last time. And at the very end, last time, we were talking about term-by-term integration and differentiation of power series. Term-by-term integral and differentiation of power series. What that means is if you have a power series already, you can take the integral term by term to create another power series. And this is what we did towards the end last time. So we had, I'm not going to write down all the details of this, but we had a series for 1 over 1 plus x. It looks something like, this is an alternating harmonic series, 1 minus x plus x squared minus x cubed plus etc. And then you can take the integral term by term. You integrate everything. And it looks like the left side, 1 over 1 plus x. And on the right side, it's the integral of each of those things. Integral of 1 minus integral of x plus integral x squared minus integral x cubed. Dx of everything. I left out the dx's, but I hope you all know what I mean. You can take the integral throughout the whole thing. The integral on the left side ends up being a natural log. You really, if you want to write all the details out, you would do a u substitution. But anyway, it amounts to the natural log 1 plus x on the left side. And then on the right side, you do all those little integrals. What you get is the integral of 1 is x. The integral of x is 1/2 x squared. The integral of x squared is 1/3 x cubed. Each of these is just doing the integral. The integral x cubed is 1/4 x to the 4, etc. And unfortunately, you get a plus c when you do this integration term by term. And really, that's usually we write the plus c at the beginning because it's kind of low class to put something after the dot dot dot. The dot 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 means this goes on forever. But then you also have an extra constant. And this is just a quick version of what we were doing at the end last time. If you plug in x equals 0, what happens? I mean, just plug in x equals 0 everywhere on both sides. On the left side, it says ln of 1 plus 0, which is 1. And what do you get on the right-hand side when you plug in x equals 0 everywhere? Just c. Yeah, all of this stuff is just 0, 0, 0, 0 every time, but the c, of course, the c remains. So this says a bunch of zeros, but then you get this extra c. All right? And you can use this to solve for c. That just means c equals ln of 1. And what is ln of 1? It is 0. Yeah, so that means 0 equals c. And so that thing that I wrote up there with the ln, I'm going to just write that again, but the c actually is 0. You don't have to consider the c at all. X minus 1/2 x squared plus 1/3 x cubed minus 1/4 x to the 4 plus blah, blah, blah. There is no c, the c equals 0, so you don't need to include it. All right. This is a power series for the natural log. In particular, it's the power series for ln of 1 plus x. And it's a very, I would say, very nice looking formula. You know, it has a very simple pattern to the way that the coefficients go in front of the x's. This is a power series for ln of 1 plus x. Now, it's a little weird that this is ln of 1 plus x. Wouldn't it be nicer to just have a power series? So what about just ln of x? I mean, that's when people talk about the natural log function, they mean this. They don't mean this. This ln of 1 plus x is a weird, I suppose it's translated, right? It's like this kind of, what's the difference between these two pictures? 1 plus x in here has the effect of horizontally shifting the graph. Maybe I'll just draw that. So ln of x, the normal natural log function looks like this. This is ln of x. ln of 1 plus x is the same thing shifted to the left or to the right. I think it's to the left by 1. So this one looks like it goes right through the origin, like that. This is ln of 1 plus x. Right? And that, you know, in the original picture, this y-axis is a vertical asymptote. In this picture, this would be a vertical asymptote, right? So what we have is a series for this one, but not a series for this one. And there's a reason why, actually, the one on the left doesn't really have a series of the format that you see up here. This is a power series. Some terminology we talked about very briefly once, but it's going to become more important. This is a series, what we call centered at 0. This centering business, remember, is because the series on the right side of the equal sign is powers of x rather than powers of centered at, this is just refreshing our memory. Sorry, I'll have to write it down here. centered at, say, A is powers of x minus a every time. And what we have at the top there, sorry, it's gone now, is centered at 0 because they're powers of x, just x, which you think of as x minus 0. All right. But anyway, the reason I'm saying all this is because this function over here, you really can make a power series centered at 0 because at 0 here, there are nearby points. Remember, every power series like this, it converges in some interval around the center, which in this case is 0. And there's an interval around 0 where it converges. No problem. This one, this is a problem though. You cannot make a series for this centered around 0 because 0 is a vertical asymptote. And so it's not even possible for this to converge when it's centered at 0. So that's why this ln function has a series centered at 1. That's why it's x minus, well, it's, yeah. It does have a series centered at 1, but not centered at 0. So that's why there's sort of no series for ln of x, but there is a series for ln of 1 plus x. All right. All of this is, I'm trying to explain why you can't actually get a satisfying power series for just ln of x. It's because ln of x has a vertical asymptote at 0, and that screws up the convergence of the series. All right, this is not terribly important, but I thought something interesting. Let's see if we can try another one of these, finding a series by doing term by term integrals or derivatives. There is a nice series for the arctan, also known as inverse tangent of x. All right. I've said a few times that, like, for weird reasons, the inverse tangent or the arctangent is actually a much nicer function than the arcsine and the arccosine. The inverse tan, it has nicer derivative and integral formulas and so on. And I'm going to use the fact that the arctan or inverse tan is the integral of 1 over 1 plus x squared, right? This is a integration formula that we have used, from time to time. And what that means is if I get a series for this, find a series for 1 over 1 plus x squared, and then do the integral, and we'll get a series for the inverse tan. That's my strategy. You find a series for 1 over 1 plus x squared, and then do the integral term by term, and then we will end up with a series for the inverse tan. So let's try to follow these steps. So let's do a series for 1 over 1 plus x squared. All right. I don't know if you remember how to do this. We were doing examples like this last time, or a couple times ago maybe. And actually, I think we did exactly that example. But you start with this series, 1 over 1 minus x. Anybody remember what that is when I write out the series? This is like the basic series, the simplest one of all. Yeah, it's just the sum of x to the n. So if I were to write term by term, it's just that. This is baby's first power series. This is the standard one that all of the other ones are based on, at least in terms of this integration term by term thing. All right, so we do that. Can we make this instead into a series for 1 over 1 plus x squared? So to get instead 1 over 1 plus x squared, we just plug in, we use negative x squared in place of x up here, right? It's because this formula says 1 over 1 minus x, and if I wanted to force it to look like 1 over 1 plus x squared, it just, instead of x, you replace x by negative x squared. This is the sort of plugging in trick. And what does it look like? So 1 over 1 plus x squared looks like, all right, I see 1. I'm just on the right side here, plugging in negative x squared instead of x. So the next term will be 1 plus negative x squared, and then plus negative x squared squared, and then plus negative x squared cubed, etc. And then just, can we simplify that a little bit? This says 1 minus x squared. And then square the next one. Can somebody say what's it going to be? First of all, is it going to be a minus or a plus? It's going to be a plus because I have this thing, I'm doing this right here, right? What's inside the parentheses is negative, so when I square it, it becomes positive. And then what about the x? It's x to the 4th, yeah. In this situation, you should be multiplying exponents. And so 2 times 2 is 4. That's where we get the 4. All right, the next one, I have a third power, negative on the inside, but a third power. 3 being odd means that this ends up being negative still. And then it's going to be x to the power 6. And maybe you can see the pattern here. This is going to be alternating signs and even powers every time. All right. And so this is a power series for 1 over 1 plus x squared. Okay? Could we write that as a summation? This is probably easiest if I use a sum starting n equals 0. Anyone want to suggest? There's going to be kind of, well, there's really just powers of x and then the signs alternating. How do I get the alternating sign? Yeah, negative 1 to the n. And then I want to say powers of x. X to the. Now you want to make it so that all the powers end up even. Anybody got a cute trick to make that happen? If I said x to the n, then it would look like, x and then x squared and then x cubed. I don't want that. I want only even powers here.
To 2n?
Yeah, if I go x to the 2n, that makes all the even powers. Yes, great. All right. Anyway, all of this, really my true goal is to do the integrals. Now do the integral term by term. That means you just do the integral every time for all of these things on the right-hand side. Equivalently, you do the integral on the inside of the summation. So it becomes integral 1 over 1 plus x squared dx is the sum, n equals 0 to infinity, integral minus 1 to the n, x to the 2n dx. All right, and we have to try to do these integrals. What do you get on the left side? Something I said a few minutes ago. Yeah, that's the arctan. That was kind of the whole purpose of this, was that eventually we're going to end up with a series for the arctan, also known as inverse tangent. And on the right side, it's going to be sum n equals 0 to infinity. And when I do the integral over here, this is weird, the integral inside of a sum, but it's really just focus on this part right here. Do the integral, and the n you treat as if it were a constant inside of this integral. So minus 1 to n is just going to stay like it is because that is just a constant. And then x to the 2n, I use the integration rule about, x to some power. You increase the power by 1, and then you divide by the new power in a fraction. So I'm going to say this is 1 over 2n plus 1, x to the 2n plus 1. Like that. That's the integral. And then all of this also has a plus c. And like we did just a few moments ago with the log, you have to calculate the plus c yourself by plugging in a convenient value, which is usually x equals 0. That's typically how to do it. All right, so let's find the c. Find the c. I'm going to plug x equals 0. On the left side, it says arctan of 0, which you have to think about what that is. And then we have the sum, minus 1 to the n, 1 over 2n plus 1 times 0 to the 2n plus 1 plus c. And what is the sum? Those are all zeros. What we have is a sum of a bunch of stuff, but all this stuff here is something times 0. So everything inside the sum is 0. So everything on the right-hand side just equals c. And on the left, what is the inverse tan of 0? That means I want to know what is the angle so that when you take the tan of something, it equals 0. I give you one guess. Yeah, it's 0. The tan of 0 is 0. So the arctan of 0 is 0. So this says 0 equals c. So again, in this example, so c is 0. All right. And my final answer then is this is a series for the inverse tan. It's just what I said before, only you can leave out the plus c, because the c equals 0. All right. And what you see here, if you were to write out the terms, like if I just wanted to write these out to see kind of what it looks like with the coefficients and all that, what I see here is alternating, first of all, and then powers of x which are always odd. If it said x to the 2n, that would be even powers every time, but instead it says x to the 2n plus 1, which means odd powers every time. So we begin with x to the 1, and that one will be negative because the alternation makes, that one will be positive. So when n is 0, you get positive sign, but then this equals 1. So the alternation goes positive first and then negative. And it'll say 1/3 x cubed plus 1/5 x to the 5 minus 1/7 x to the 7, etc. All right, this is the inverse, the series for inverse tan. I'll put that in a box. I don't think you need to memorize this, but for the sake of having in your notes, you should have sort of a collection of series of various well-known functions. And this is a fairly important one, the arctan. All right. Any thoughts about that? This, again, I think is a fairly nice formula for a function which, I was trying to impress on you all at the end last time. There's something really very, to me, there's something very beautiful about this kind of power series formula. He's not into it. Sorry. Because it kind of reveals a hidden nature of the arctan function. I don't know what if you all have like feelings about arctangent deep down in your heart about what the arctan means to you personally. But this is something that this way of looking at what the arctan is something that is not at all obvious based on like, if all you know about is trigonometry and like what the arctangent means, you would have no reason to think that the arctangent is also equal to this. There's really no, and the people who created trigonometry had no intention of making something that equals this. But this is kind of the true hidden nature of the arctangent function, which is very interesting in my opinion. All right, so we have a few different basic functions with series, but I want more power series for more functions. Series, the plural of series is series. But I would like more power series, like for any function you can imagine. For e to the x, sine of x, cosine x. How about tan? You know, the real tan, not the arctan, etc. When people discovered power series was a thing, immediately people started trying to figure this out. What are power series of all your favorite functions? And this is another thing that you can see like in big lists of things in the back cover of your math book. You know, there's a big list of derivatives and integrals. Oftentimes you will see a big list of power series for all your favorite functions. And actually you can't get these by doing term by term integration of the ones we've talked about already, because they can only go so far. Like we just sort of got lucky that this arctan, we could somehow relate it to 1 over 1 plus x squared. But that's not true of these other functions. So we are going to talk about a general purpose way to find the series of any function. By any, I don't actually mean any. I mean more or less any function which you can take the derivative of. So differentiable. Technically, you have to be able to take the derivative over and over again. So not just the first derivative, but if you know how to find the first derivative and the second derivative and the third derivative, etc., then this general purpose thing that we're going to talk about is actually sufficient to find the series for any function, provided you know how to do these derivatives. And it's called the Taylor series. The Taylor series. All right. So here's the idea. This is actually not so hard to do once you know what's up, but I want to give us some kind of approach. So what we want to write just any old function you start with. You want to somehow figure out how to write it as a series. And of course, a power series always looks like that, right? We want to write our function f of x, whatever it is, as a series. And so when I say, how do we figure out what the series is? Really what I mean is, how do you find the coefficients? Because if I can figure out what the coefficients are, then that's what the series is. So the real question is how to find the coefficients C0, C1, etc. Right? If you know how to find the coefficients, then that's it. That's the whole game, really. And we have already talked about how to find the first one, C0. That is just like in the examples we just did, that's like the C, right? The way to find the C, this one, you can find by just plugging in x equals 0 everywhere, and everything over here will disappear, right? So you can finding C0 is easy by plugging x equals 0, right? And what can we say specifically what it'll look like? If I take this thing in the box, plug in x equals 0, the left side says f of 0 now, because I'm using x equals 0 everywhere, and the right side says C0 plus 0 plus 0, etc., right? So C0 is f of 0. So that's how you find the first of these coefficients. The constant term is always just equal to f of 0. So for instance, if I want to find a series for like cosine, I don't know what the rest of it is, but I know the first one is going to be 1, because this is equal to f of 0, and cosine of 0 is 1, so that first term must be a 1 for cosine, and it's a 0 for sine. All right, anyway, that's how you find C0. What about the other C's? And here's the trick. The other C's we find by term derivatives. All right, so I'm gonna just we can still see it in the box, right? Term by term derivatives. If I start with the thing in the box and do the derivative, what it says now on the left side, it says f prime of x, and on the right side we do the derivative everywhere. What happens to C0 when I do the derivative? It becomes 0 because it's just a constant. So C0 just straight up goes away. C1x, what's the derivative of C1x? It is C1, because the x, when you take derivative, becomes 1, and it's just C1. So that's C1 plus C2x squared. Well, C2 being a coefficient stays like it is, but when I take the derivative of x squared, that 2 comes down to the front, and it will now look like 2 C2x. Next will be 3c3x squared. The next one would look like 4c4x to the cubed. All right. Each time I'm just doing the ordinary derivative power rule. The exponent comes down to the front as a coefficient, and the exponent in these ones has to just join in with the existing coefficient. So 3c3 x squared. All right? And now we can use this to find c1 by, again, plugging in x equals 0 everywhere. Then all these guys disappear, and all we end up with is c1. So now, again, we plug x equals 0 everywhere. It says on the left, f prime of 0 equals c1 plus a whole bunch of zeros. So c1 is f prime of 0. All right. This is how we find c1. Can you remember? So you have to kind of keep this straight. Remember what I said before? Maybe I'll sort of summarize in a box over here. c0 is f of 0, right? And what I just said was c1 is f prime of 0. I'm starting to feel good about this. This is like a thing that, mathematicians, most mathematicians will identify this as some aspect of mathematical beauty, is when you are doing things and you discover patterns which are not obvious to begin with. And this certainly is an interesting pattern here. If you start with any old function and you want to create the series, how do you know what the coefficients are? The first one is f of 0. The next one is f prime of 0. Anyone want to guess what the next one is? F double prime of 0? Yeah, actually it's not that. This is a bit of a trick question. It does have to do with the double prime though. So I'm going to try and continue this list. C2 is what? All right? He's on the right track with the double prime. How would you find the next one? You would take this thing, which was the first derivative, and just do the derivative again. This will bump the C2 down to the first position, and then you'll be able to find the C2 by the same method. So from here, I'm going to do the derivative again. What does it look like now? Now the left side says f double prime of x. The right side, the c1 being just a constant goes away. The c2 was the coefficient of x, and so that stays, but it has this 2 on it. So it's 2c2, no x, because the derivative of x is 1. The next one, 3 times 2, this is going to be a 6 now, 6c3x. That 6 comes from, it used to be a 3, but then I take the derivative again, I get 3 times 2, which is 6. Next is, used to be a 4, but I take the derivative again, it's going to be 12 now. So this is plus 12c4x squared, and then some more. All right? Anyway, we plug x equals 0 again. It now says, on the left, f double prime of 0, on the right, 2c2. So c2 is 1/2 f double prime of 0. Put this in the list. C2 is 1/2 f double prime of 0. You have to remember that 1/2. What's it going to be for the next one, C3? This shall be obtained by doing the derivative again. Now, we're not just going to do this forever, but we should do this until we can figure out what the pattern is. I would say so far it's not quite obvious what the pattern is. It's going to be some derivative. It's not much of a spoiler to say. It will involve the third derivative, but there's going to be some coefficient here. Can we just try and figure this out? Let's do it one more time, and then we'll see if we can figure out what the pattern is. F triple prime of 0. The 2c2 goes away because there was no x there. The next term, 6c3, is just going to be 6c3 with no x. Followed by 12 is going to get another 2. That will be 24c4x. And then some more higher terms. And again, we will plug in x equals 0. Sorry, on the left, I shouldn't have said 0 yet. I wasn't plugging in 0 yet. So I'll keep that as x. Now I'll plug in 0. It'll say f triple prime 0 equals 6c3. To solve for c3, it is 1/6 f triple prime of 0. So this, in my tiny little chart over here, 1/6. All right? Sorry, I scrolled it. I'm going to write that again. C0 is just f of 0. C1 is f prime of 0. C2 is 1/2 f double prime 0. C3 is 1/6 f triple prime 0. Can anybody see the pattern here? I want to say generally Cn is something, I mean, it's going to be the nth derivative, which we typically write like this. So this n in parentheses means nth derivative. What about the coefficient, though? The number in front of that? What do you think? 1 over n factorial, he said. I agree. You have to think about, where did that 6 come from? The 6 came from doing the derivative a few times, which resulted in a 2 first, and then multiplied by the next exponent, which was 3. The next term up, instead of 6, which is 2 times 3, it would have been a 2 times a 3 times a 4. That is 4 factorial. The next one up would have been 2 times 3 times 4 times 5, which is 5 factorial, and so on. So this right here, if you don't remember anything else that I just said, you definitely need to remember that. This is sort of the magical formula for the coefficients of the Taylor series. They are 1 over n factorial times the nth derivative evaluated at 0. All right, and here, for this to work, this is a little weird. You can like argue with strangers on the internet about this. We use 0 factorial equaling 1. That's so that you might worry about, this thing doesn't make any sense when n is 0. But I say 0 factorial equals 1. That makes this thing make sense. And it actually equals this. So when n equals 0, you get 1 as a coefficient. And then you get like the nth derivative when n is 0, the 0th derivative. That just means like the original function itself, which is f of 0. All right. And this is actually sort of strange but true fact. In most areas of mathematics, it is convenient to define 0 factorial to equal 1. Even though from a naive point of view, that doesn't make a lot of sense. It turns out that's the way that it is most useful to make 0 factorial equal 1. I don't know what a standard calculator will say when you plug 0 factorial. I think they usually say 1 for the answer. Does it say 1? All right, so this thing that I just said in the box is the thing that you need to remember for Taylor series. All right, all of this, what I said, is about series. You had a question? Yeah?
Isn't 2 factorial 3? Because it's 1 plus 2.
It's 1 times 2.
1 times 2,
Yeah.
okay.
Yes. You want to hear a very sort of obscure fact related to what she just said? The factorial, I only recently learned this fact. Probably none of you will find this interesting, but I found this interesting. The factorial, like 4 factorial is 4 times 3 times 2 times 1. This is called factorial. Anybody know where the word factorial comes from? It's because those are factors. 4 times 3 times 2 times 1. You're multiplying here, and so these numbers individually are called factors. People don't say this anymore, but if you read like 200 years ago, people also talked about something called the termial. And I think this was written with like the hashtag. The termial is this with a plus. That is a thing, and it's called the termial. Why termial? Because when you add things, those are called terms. When you multiply them, they're called factors. Yeah. I don't know why nobody talks about termials anymore. They talk about factorials. Factorials are, I guess, just much more useful than termials. I feel silly even saying it. All right. Let's. So what I was just saying a moment ago was all this that we've talked about so far is for series which is centered at 0. All right. When you're trying to make a series which is centered at 0, the coefficients are given by just plugging in 0 to the various derivatives of your function. You can go through all those same arguments again, doing centered at some other point. I don't want to go through all the arguments, but I'll tell you what it amounts to. If we want centered at some other point, if we want centered at A, then it looks like, I'll just skip to the answer. It looks like, my function here, instead of powers of x, I write it in terms of powers of x minus a. So the series looks like this. These are powers of x minus a. And the formula for the coefficients now looks like Cn equals 1 over n factorial f nth derivative at a. So this is the difference between centered at a and centered at 0. The series looks like this. Instead of just x's, it's x minus a's. And the coefficients, instead of f nth derivative at 0, it's the nth derivative at a. This is the only difference. So centered at a really just, it sort of makes it so that there's an a in there instead of a 0 in the one that we were just talking about. So centered at A is like slightly more complicated, but not really. You just have to know to use this very slightly different formula. All right? And so I'm going to sort of summarize this as a big theorem. This is called Taylor's theorem, which I'm sure is like one of the most important theorems of the, I think this was done in the 1700s. Taylor's theorem, this is about power series, and it says if you have any function, if f of x is any differentiable function, and by differentiable I mean you can take every derivative, not just one derivative, but the second derivative, third derivative, they all exist, and you know what they are. If f of x is any differentiable function, then the power series centered at A is f of x equals c0 plus c1. This is just what I wrote a moment ago. I'm just writing it all in a nice little package here, where Cn is 1 over n factorial nth derivative at A. All right? And this is called, this right there, this is called the Taylor series. Of f of x centered at A. All right? This is Taylor's theorem, one of the great achievements of sort of early calculus. What's great about this to me is, like I said, it gives you a whole other kind of universe of discovering things about functions that you never knew about. Another completely different way of thinking about sine and cosine and whatever other function you have in mind. You can think of them as power series rather than whatever else they are, right? One important, like I said, the centered at A business is just like a weird technicality. Usually we're going to do centered at 0, and there's a special name for that. So when we center at 0, it's like everything becomes a little bit simpler. It's not a big deal, but it's c1x, c2x squared, where the constants Cn is 1 over n factorial nth derivative at 0. And this is called, I actually don't say this very often, but it's called the Maclaurin series. This is just the name of another guy who I guess loved centered at 0. So the Maclaurin series, if you hear somebody say that, it means the Taylor series centered at 0. Although I myself usually would just say the Taylor series centered at 0. Or just the Taylor series. I mean, if nobody says where it's centered, usually they're talking about centered at 0. This is called the Maclaurin series. All right. A few years ago, there were some hilarious math memes that said something like, they had this, and then they said this is like the this is the series, and then this is the series Taylor's version. Get it? I didn't get that at first. When I first saw this is hilarious math. The intersection of people who know some advanced calculus and also know about Taylor Swift's copyright disputes with her record company. All right, that's the Taylor version, and the other one is the Maclaurin version. All right, one thing that I haven't mentioned yet that everybody knows, though, every series that you write has a certain radius of convergence, or it has an interval of convergence, and that interval, its center is the center. So if you're doing a Maclaurin series, then the interval will be centered around 0. If you're doing a Taylor series like this, it'll be centered around A. But I will just say each one has a radius of convergence. And we talked last time about finding the radius of convergence. There's some problems on the homework about that, but so we don't need to get into the details now. But just to remind everybody, each one has a radius of convergence, and typically you find it using the ratio test. You can actually use any of the appropriate tests, but the ratio test is usually the one that works nicely. All right. So this is the theoretical idea. That was a lot of talk just to end up with this formula in the box. But this formula in the box is fairly easy to apply and use to actually find the series of all your favorite functions. So let's find the series. Let's find the Taylor series at 0, otherwise known as the Maclaurin series, for e to the x. This is like one of everybody's favorite functions from calculus. All right, so in this case, our original function, I'm just going to use the various things in the box from above. I start with my original function being e to the x, and we'll need to know the nth derivative plugged in 0, right? Because that's what the various c's, those coefficients are. They are determined by the nth derivatives. For certain functions, this is kind of hard to do. You have to somehow figure out, what am I going to get if I take the derivative over and over again? For this one, it's very easy. But anyway, f prime of x is e to the x. The second derivative is also e to the x, right? In this particular example, this is like the easiest Taylor series to do. Every derivative is just equal to e to the x again, right? So here, the nth derivative at x is e to the x. So the nth derivative plugging in 0 is, what do you say? 1. Yeah, it's e to the 0, which is 1. And this is 1 for every n, right? In a typical example, you'll get different answers for different n's, but here you get the same one every time. Usually this is the hard step, because you have to somehow figure out a formula for what you get when you take the derivative over and over again, which is, in the case of e to the x, very easy, but in the case of other functions, it might be much harder. But for e to the x, it's very easy. So that means Cn is the formula 1 over n factorial f nth derivative at 0. But that nth derivative thing we just said equals 1, and so all you get is 1 over n factorial. And this is basically, this is basically your final answer. So the series then, e to the x is, I can write it as a summation, 1 over n factorial x to the n, where n goes 0 to infinity. Right? Because this right here is the coefficient each time. 1 over n factorial x to the n. If you want to see what the terms look like, this is very simple. The 0 term is 1, and then you get 1 x to the 1. Then you get 1 over 2 factorial x squared, 1 over 3 factorial x cubed, 1 over 4 factorial x to the 4, etc. This is e to the x. All right. Again, this is, in my opinion, a very nice formula for e to the x. Really there's something kind of beautiful about how simple the formula is. I mean, it has factorials, which are slightly weird, but otherwise, it's about as simple as you could hope for. All right. This, if you're ever talking to your little sister about, your 8-year-old sister asks you, what is that thing, e to the x? This is like the worst way you could explain to a kid what e to the x means. It means this. It's like you add numbers together forever, starting with 1 and then x and then x squared, but you got to divide by 2 factorial and so on. If you explain this to a kid, you're not wrong. It's not a great way to explain what e to the x is supposed to mean. But actually, a smart kid could say, oh, okay, that means like e to the 0 is 1, right? Actually, you can see that very clearly from the series, even if you have no idea what e is or what e to the x means. E to the 0 must equal 1 because when I plug in 0 here, I get 1. So you can see weird properties of this function, even if you don't know anything about what the function is supposed to be, just using this series here. All right, this is e to the x. Can we just, as an example, let's find the interval of convergence. I got one of these for you to try in a moment. Can we find the interval of convergence? This we haven't done yet today, so it's been a while since we did this. But like I said, you should use the ratio test. The rat test. The ratio test. I hope everybody remembers something about the ratio test. That's the one where you have this L, which is the lim n goes to infinity of the ratio an plus 1 over an. And it converges when the L is less than 1, and it diverges when the L is more than 1. And so this, you can just sort of figure out what it is. Now, what is an plus 1 and an? They are this, right? Using n or n plus 1 as appropriate. So in this example, an is 1 over n factorial x to the n, right? And so when I plug in here, absolute value, an plus 1 looks like 1 over, maybe as usual, I usually write this as multiplication times the reciprocal, so I don't have to deal with fraction inside of fraction, right? There's that, and then that was an plus 1, and then times the reciprocal an, that would be n factorial over x to the n, right? And then we try to simplify this however we can. I see x to the n plus 1 and x to the n. Those will cancel, giving me just absolute value x, right? Because I have an extra x in the numerator. And then what about the factorial bits? N factorial divided by n plus 1 factorial. Anybody remember how to, I'll write that down. This I can pull out of the absolute values because it's always positive. Anyone remember, do I cancel the exclamations? No. You remember what's the appropriate thing to do here? You have to remember the top represents 1 times 2 times 3 all the way up to n. The bottom is 1 times 2 times 3 all the way up to n, and then to n plus 1. So if you think about it in terms of the factors, almost everything can cancel in this, right? This thing here looks like 1 times 2 times 3 up to n, divided by 1 times 2 times 3 up to n, and then n plus 1, right? And here, in this fraction, everything will cancel except the n plus 1 on the bottom. So this whole thing just looks like lim n to infinity, absolute value x times 1 over n plus 1. This is how you can simplify factorials like that. All those guys cancel except the n plus 1. All right, and what is this limit? You consider the x like a constant when I take the limit. I take the limit of n. What do you get? 0. Yeah, this equals, I mean, you could say absolute value x times 0, which is 0. So L is 0, which means it converges no matter what the x is. It converges for any x. So in this case, the interval of convergence, this usually doesn't happen, but in this case, the interval of convergence is straight up. You could say all real numbers, or it's the interval from minus infinity to infinity. If you look at our examples from a couple times ago, you'll see usually it doesn't go this way. Usually it gets some actual sort of specific interval, but here it's all real numbers. All right. Can we try one more? I had one more, and then I wanted you guys to try one. Let's just try one more altogether. Maybe there'll be enough time for you all. How about the series for sine x? I want to try and do all the same stuff. Here it will be a little bit more complicated, but not so bad. Again, the important part is those derivatives at the beginning, which for the sake for the example of e to the x, those derivatives were very easy, but in any other example, that's going to be the hard part. F prime of x, I'm sure we all know, is cosine x. F double prime of x. You need to somehow write down a bunch of derivatives and figure out what the general pattern is. Here it would be negative sine x. F triple prime is negative cosine x. These are just like different every time, unfortunately. I want a pattern. The fourth derivative. What's the derivative of negative cosine? Positive sine x, yeah. Okay, the fifth derivative, the derivative of sine is cosine. Actually, now I see there's a pattern. The pattern is basically these four repeat, right? It goes sine, cosine, negative cosine, and then back to sine. And then it'll go sine, cosine, negative cosine, sine, cosine, negative cosine, and so on. So it just repeats those four things in that order over and over again forever. All right? Okay. What I'm looking at is plugging in 0 every time, right? F prime of 0, F double prime of 0, because I'm trying, that's what gives me those coefficients, right? So these you just have to, knowing what you know about sines and cosines. Sine of 0 is 0. Cosine of 0 is 1. Negative sine of 0 is negative 0, I suppose. Negative cosine of 0 is negative 1, and so on. These will continue the same pattern. 0, 1, 0, minus 1, 0, 1, 0, minus 1, etc. All right. This one actually is kind of hard to write a formula for, but I can still write the Taylor series. So the series, this is actually the Maclaurin series because I'm doing centered at 0. It is sine x is, okay, the first term is 0. The next term is plus 1. I also need 1 over n factorials every time, right? But anyway, that's still just 1. X. Next, I have 1 over 2 factorial times 0 x squared. And then 1 over 3 factorial times negative 1 x cubed. This is the pattern. The coefficients go 0, 1, 0, negative 1. And you also always need to include these factorials in fractions. All right? So it's a little hard to say what exactly do the dot, dot, dot mean. The dot, dot, dot means you continue this pattern of 0, 1, 0, minus 1. And you also include the factorials, 0, 1, 0, minus 1. Now, half of these are going to be 0, right? All the way down the line. In fact, you can see every even power of x will get a 0 on it. The odd powers of x will get plus, some of them will get plus 1s and some will get minus 1s. So you can write this, just simplifying a little bit, it's x is the first one. Then I have x cubed, and that's going to be minus. So it's minus 1 over 3 factorial x cubed plus the next one will be, the next odd term is the 5th. Then the 7th is the negative, etc. So this is the pattern. Maybe it's a little easier to see the pattern here. What you get are alternating terms, odd powers, and every time 1 over n factorial in the front. Again, this is not such a difficult pattern to come to terms with. That is what sine of x is. That's the power series for sine of x. And again, if you're talking to a little kid, they ask you, why is sine of 0 equal to 0? Worst possible answer, it's because the Taylor series of sine looks like this, and if I plug in x equals 0 on the right-hand side, everything is 0, and so that means sine of 0 equals 0. That's true. You can actually determine many of the properties of sine of x just straight up using this series expansion, even if you don't know anything about sine of x, what it really means. All right? Could I have you all, we got 10 more minutes, can you find a series for cosine? It will end up pretty similar, but all the patterns are slightly different. So see if you can find the series for cosine x. It will be much the same as what we just did, only all the details are just a little bit different. Start with cosine. No, this is the example we just did. Yeah, so you have to start by taking all these derivatives, which will be somewhat rapid derivatives. Like you're going to start with fx equal cosine x, and f prime is something else. Okay. I'm going to write down what I got. I want to talk about the convergence also. Look like people are doing fine. Can we just talk about this? Because I want to just say what the convergence interval is too. So we start with cosine. You do the derivatives, and they, again, have this kind of repeating pattern after 4 of them. The fourth derivative will be cosine again, right? So when I plug in 0 each time, I get 1, and then 0, and then -1, and then 0, and then 1 again. So it's really the same as the sine, only here we start with 1, 0, -1, 0, whereas up here we started with 0, 1, 0, -1. So it's really just the same thing, but sort of shifted by one position. Anyway, so that means that C0 is 1, C1 is 0, C2 is 1 over 2 factorial times -1, C3 is 0 again, C4 would be 1 over 4 factorial times +1, etc. So the terms, when you write the series, it looks like 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4 minus 1 over 6 factorial x 6, etc. So the cosine has even terms. In this way, the sine and the cosine actually they look great together. They make a cute couple, I would say. They are basically the same thing, but with even versus odd powers. All right. Each of them have alternating signs. The only difference really is the cosine has all the even terms. The sine has all the odd terms. Very cute, in my opinion. Anybody? Perhaps you've heard that cosine is what we call an even function, and sine is what we call an odd function. And probably you know what that means, but here's another way of knowing what that means. Actually, an even function is one where all the powers, all the non-zero terms of the Taylor series are even, and an odd function would be one where all the non-zero terms of the Taylor series are odd degree. Hidden connections beneath everything. It also suggests, something this suggests to me is somehow, I don't know if you ever thought of this, if you add these together, like this one has only the evens, this one has only the odds. If I add them up, I get all of them, right? And is that anything? I would say that's kind of this, isn't it? I didn't put a box. This deserves a box, don't it? It's the same thing with the 1 over whatever factorial. If you add these together, the only difference is this alternating signs, right? Which the e to the x doesn't have the alternation. If it weren't for this alternating signs, then it would be true that like sine of x plus cosine of x equals e to the x. Wouldn't that be wild? We do not live in such a universe, because when you add these, you don't get all positive signs. You get some being positive, some being negative. Anyway, can we just in 3 minutes talk about the convergence, because this is important. Let's talk about the convergence let's just talk about cosine just because that's the one that we just did. It's actually the same for both of them. So for cosine of x, now this one is a little weird to write. It's not so bad. To write this as a summation would look like 1 over n factorial. Sorry, it's only even powers. So the cosine I would write this way. 1 over 2n factorial minus 1 to the n x to the 2n. That's the series if you want to write it using the summation sign. It's only even powers and only even numbers inside the factorial. So that's why I have 2 n's there instead of n's. But to get it to alternate, you actually still need just n here, not 2n. If you put 2n, it'll be positive every time, which you don't want. Okay, anyway, let's do the ratio test. I go L is lim n goes to infinity, absolute value an plus 1 over an, right? Hopefully this will just sort of simplify nicely. Okay, an plus 1 is going to be that thing that you see inside the summation, but with a plus 1. So it's 1 over 2n plus 1 factorial minus 1 to the n plus 1, and then x to the power 2. Sorry, I wrote 2n plus 1. This is not quite right. It should be 2 and then parentheses n plus 1 right here, because I'm replacing n by n plus 1. 2 parentheses n plus 1, which really means 2n plus 2 if you distribute. And same up here in the exponent, all right? And that's an plus 1. Now I go times the reciprocal of an, which will look like 2n factorial up top and on the bottom, minus 1 to the n x to the 2n. All right? Can we simplify? Sorry, now it's time to go. Will you give me a minute? I usually let us go a couple minutes early, so you owe me. All right? First of all, there are not -1 to the n's or whatever. Those don't matter because everything is inside of absolute value signs, so we don't really have to care about the signs of those. We have various factorials. I have 2n factorial on top, and on the bottom, 2n plus 2 distributing there, factorial. And then as for the x's, I have x to the 2n plus 2 up top and x to the 2n on the bottom. I'm distributing the 2's like that. So what will cancel? As far as the x's, I end up with x squared in absolute values. And as far as the rest of it, actually we don't need the absolute values for the first part because that's all positive. Again, up top we have 1 times 2 times 3 up to 2n. On the bottom I have 1 times 2 times 3 up to 2n plus 2. That will cancel everything, but we remain with that. Right? Everything on the bottom cancels something on the top, but there's 2 extra things on the bottom. They are 2n plus 1 times 2n plus 2. But anyway, when I take this limit, that part becomes 0 because it's degree 2 on the bottom and constant on the top. So this equals 0. That means the interval of convergence is all real numbers because the L is always less than 1. So these series, we did this for cosine. It's the same for sine. The details work out the same way. They converge for all values of x. All right, we'll do a little more.